So they've told us that x1 equals 1, x2, oh, I see, so x1 equals 1, and x2, so n sub n plus 1 equals the sum of the first n things. So x2 equals x1, right? So sorry, I should write that. So here's what they've given us. They've given us x sub n plus 1 equals x1 plus x2 plus all the way to x sub n. Is that right? Yeah, that's what they've written there in the problem, literally. So that means x sub 1 should equal 1. That's what's given. And then x sub 2 equals x sub 1 plus all the terms up to x sub n, which is just x sub 1. I have a guess as to what this is, but we will see. So then x, oh no, I don't have a guess. I thought I had a guess, but it's wrong. My guess was the Fibonacci sequence, but I don't think it's actually that. So then x sub 3 is x1 plus x2, which is 1 plus 1, which is 2. And then x sub 4 is the sum of the previous 3 terms, so it's 1 plus 1 plus 2. So I'm just going to write out that it's 4. All right, so basically I'm just adding up all these numbers. So 1 plus 1 is 2, 1 plus 1 plus 2 is 4. And then x sub 5 is looking like 1 plus 1 plus 2 plus 4, which is 8. This seem right? Seems right to me. Looks like x sub 6 is 16. So it looks like the numbers are powers of 2, I think. Maybe not the first couple. Well, I mean, they are, but like, so here's what I would say. All right, because then the next one's going to be x sub 7 is 32 and so on. So this is 2 to the 0th. This is 2 to the 0th. This is 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th. So it looks like, at least for the later terms, the power of 2 is 2 less than the index. So I would say that x sub n is equal to 2 to the n minus 2. And that's true for, I think, everything except for the first term, right? So x sub 2 is 2 to the 2 minus 2, which is 2 to the 0. X sub 3 is 2 to the 3 minus 2, which is 2 to the first, which is 2. Yeah. So here's what I would say. I would say that I would write it like this, I guess. X sub n equals 1 for n equal to 1, and 2 to the n minus 2 for n greater than or equal to 2. That's how I would write it. Oh yeah, and they clearly say that in the problem. They say write out enough terms to deduce a general formula for xn that holds for n greater than or equal to 2. So here is the formula for n greater than or equal to 2. That's not too terrible, but yeah, I definitely had thoughts about what it was going to be. I had 2 thoughts, both of which were totally wrong. But if you write out enough terms, it becomes pretty clear that, oh yeah, the next term is just the sum of all the previous ones. I feel like I'm like, is that really right? I have to double check here. X sub 3 is 1, x sub 4 is, yeah, this should be right. Yeah, that's right. Sometimes you have to convince yourself. You're like, did I do something stupid or is it the right? No, I think that's the right thing. Okay. Yeah, that's a good question. It's fun. I like that. Let me go ahead and grab my notes. They are right here. So I'm going to start. I know last class we talked about the comparison test briefly. I just want to remind you guys kind of what we have so far. So here's, at least from me, here's what we've got so far. We know that for the sum from n equals, it doesn't really matter where you start, but we often start at 1 to infinity of a sub n. Here's what we have so far. We have the test for divergence, right? If the limit as n goes to infinity of a sub n is not 0, then we know that the series diverges. Again, called the test for divergence because it only shows you if something diverges. It never can say anything about if a series converges. And then we briefly talked about the geometric series, right? If you have your sequence equal to some a times r to the n, right? So if your series is the sum of a times r to the n, this converges if your ratio is between 1 and -1, diverges if your ratio is bigger than or equal to 1 or less than or equal to -1. We also have the integral test. Basically, the way I like to think of the integral test is the fine. Words, gotta write some words. If a sub n is equal to f of n, then the series for a sub n and the integral from 1 to infinity of f of x both do the same thing, have the same behavior. So if you can see that the integral from 1 to infinity, or wherever the thing starts, like if this started at 3, start at 3. If this converges, that converges. If this diverges, that diverges. And lastly, the last kind of test that we started talking about, which I'm going to continue on talking about today, is the comparison test. That's not true. There was one other test. There was the p test, which says that the sum of 1 over n to the p from n equals 1 to infinity converges if p is greater than 1, diverges if p is less than or equal to 1. And lastly, so far, we have the comparison test. I'll write on the other side because that's what we're going to look at today. So the comparison test just says that if your series is bigger than the series that diverges, your series also diverges. If your series is smaller than the series that also converges, then your series converges. That's the whole deal. So let's look at some examples. And often I will say, typically when we are using the direct comparison test, we are almost always comparing, not always, but often we are comparing to known p series that converge or diverge. That is usually where I'm going. I really wish there's something covering up my face on my screen, and I know it's not that big a deal, but it's weird to look at my face and see like my eyes just covered up and the rest of it just, it's a little disconcerting. I don't like it. It's just because of where I'm standing. Oh well. Okay, so let's look at a couple examples. Then we'll write the test. I imagine you guys might already know it, but here we go. So the sum from n equals 1 to infinity of 1 over n cubed plus 2. Basically, when you're thinking, well, if you're thinking about which test to use, I guess first we should talk about what tests we have. Nth term test doesn't tell us anything here. We know that this series is, the sequence 1 over n cubed plus 2 goes to 0. And if the sequence goes to 0, we don't know anything. It's not geometric. It's not p series, although it looks very much like a p series, right? This is certainly very similar to just 1 over n cubed. It's not exactly the same. So we can't use a p test unless specifically it's 1 over n to a power, nothing else. And then we can't use the integral test because I'm pretty sure it's really hard to integrate this. It might be possible. It's possible to integrate that, but you have to factor the denominator. I know it seems like you couldn't factor that, but you can. It factors really dumbly. And then you have to use partial fractions. You do not want to do that, right? If you're starting to say partial fractions when you're doing an integral, you should not be thinking of the integral test. So it's almost a p series. In fact, we're going to compare it to, so we're going to compare this to the p series from n equals 1 to infinity of 1 over n cubed, which we know converges. Okay, so here's the thing. A lot of the time, if you're trying to use a test, you already have to have an idea. We think it converges, so we're going to compare it to something that converges. Or we think it diverges, so we're going to compare it to something that diverges. If you think something converges and you're comparing it to something that diverges, you're not going to get anywhere. So let's see what happens here. I'm going to not use the limit comparison test. I'm using the direct comparison. So here's what we need to be true for the direct comparison test to work. If you're looking for convergence, the sequence of the unknown series, so we need to observe that our sequence, 1 over n cubed plus 2, every term of this sequence is less than every corresponding term of this sequence. Which is true, right? This denominator got bigger, so this fraction is smaller. And it is also required that the terms of the sequence all be positive. That's also a requirement. So then here's what that says. It says that if this is true, and it is, then it is also true that this series, how do I want to say this? Yeah, I'm going to say it this way, is definitely, I kind of write that a little bit lower. But basically, we know that this sum from n equals 1 to infinity of 1 over n cubed plus 2, we know that that sum is certainly positive, but it's less than this. But this we know is convergent. And if I'm less than some finite number, I'm also a finite number. There's a little bit more going on here. It's really the case that, right, this sum is getting bigger and bigger each term. So you have something, right, the sequence of partial sums is getting larger every term, but it's got an upper bound, which is whatever this is. So as you might have heard me say before, or as your teacher might have said, if you have a monotonic sequence that is bounded, then it has to converge. The sequence of partial sums is monotonic, right? Here if I start writing out terms, I get 1 over 3 plus 1 over 8 plus 2 is 10, 1 over 29, and so on, right? Each partial sum, here's S1, here's S2, here's S3, right? Each partial sum is bigger than the previous one. Is that supposed to be 1 over n cubed? Yeah, you're right, it is. Good call. Thank you so much. You were definitely right. It is supposed to be 1 over n cubed. And so you can see here that the sequence of partial sums is increasing, right? Every next partial sum is bigger than the previous one, but every term is still smaller than this thing here, which is a finite number. So that means, so we can conclude that the sum from n equals 1 to infinity of 1 over n cubed plus 2 converges. Great. On the other hand, and so the idea really for this direct comparison test is you're usually looking to compare against something we know. So for example, if I was looking at the sum from n equals 2 to infinity of n over n squared minus 1, I know it's not exactly a p-series, but it's a lot like n over n squared, right? Essentially, I'm usually just going to look at the highest power in the numerator and the denominator if it's a rational kind of function. So I'm going to compare to the sum from, we're going to say the sum of 1 over n. And so here's what I see. I see that, and I know that diverges. N over n squared minus 1 is bigger than n over n squared, right? This denominator is smaller, this fraction is larger. But n over n squared is just 1 over n. So it's true that the sum from n equals 2 to infinity of n over n squared minus 1 is bigger than the sum from n equals 2 to infinity of 1 over n. Okay, question. Does this diverge? Yes. Now, sometimes people get picky about this. This diverges, and I personally would say it diverges by the p-test because it's 1 over n to the first, and it doesn't matter that we're missing the first term. But some people are very, very particular because I think the p-test technically says, let me double check in my textbook here just to be absolutely sure. I got something in my eye. Sorry, one sec. Oh, it's terrible. Sorry, let me look at the, but son of a gun. Okay. I'm all right. It's okay. There's just a little something in my eye. Oh, where'd you go? Where are you, p-test? Sorry, 1 second. I just want to make sure I say this exactly right so that I'm not giving misinformation. Yeah. Sure. Interval test. Okay. Yes, interval test. Oh, come on, really? Sorry, guys. Just 1 sec. Usually they write the p. So the book does specifically state it shows that the p series where the sum goes from n equals 1 to infinity of 1 over n to the p diverges if p is less than or equal to 1, converges if p is greater than 1. So the thing is, and this is something you should take to heart, you can always cut off as many terms or add on as many terms as you want, and you won't affect the convergence or divergence, right? If this diverges to infinity, right? Add all these things up, it gets infinitely large. If you subtract off the first one thing and start here, it's still going to diverge. If you really want to, you could add 1 to both sides and then say, well, this diverges, so 1 plus thing diverges. But I think we can just say which diverges. So the sum from n equals 2 to infinity of n over n squared minus 1 also diverges. And I would really, really emphasize that if you know a series is convergent, you can cut off as many terms as you want and it still converges, right? So if you know the sum from n equals 1 to infinity of 1 over n squared converges, then so does start anywhere you want. The sum from n equals 80 to infinity of 1 over n squared also converges, right? You've just subtracted off a finite number of things. Adding or subtracting a finite number of finite numbers is never going to change whether something adds up to a finite number or adds up to an infinite number. Which is useful. We definitely use that. So this leads us to the statement of the comparison test. And I will say, we don't always use the comparison test. We sometimes do, but usually the limit comparison test is actually a better test. Well, let's go ahead and write it down anyway, because it's good to have it. So here's the direct comparison test, which you will usually just call the comparison test. And it says the following. So it says, if this, I kind of write it this way. So if an is, sorry, I need something else. If 0 is less than a sub n is less than b sub n, and the sum of b sub n converges, then the sum of a sub n also converges. And then we can also say if a sub n is bigger than c sub n, which is still should be bigger than 0, and the sum of c sub n diverges, then so does the sum of a sub n. So essentially what I said before, right? If we are smaller than anything that is convergent, we're also convergent. If we're bigger than a thing that's divergent, then we're also divergent. So the hard part is coming up with what to compare something with. Because sometimes it's easy, sometimes it's really, really stupidly challenging. Now here's a couple easy examples. So if I look at the sum from n equals 1 to infinity of the square root of n over n squared plus 5n plus 15, and I'll say this probably multiple times, if you're looking at rational functions, you're typically just looking at the highest power. And I guess technically this isn't rational. A rational function has a polynomial on top of a polynomial. But if you're looking at things where it's just powers of n over powers of n, then you're just always going to look at the highest power. So I can see that, okay, this is less than the sum of the square root of n over n squared. How do I know it's less? Well, because this denominator is bigger, so this fraction is larger. Or this fraction is smaller, so this fraction is larger. But that's equal to this. The sum of 1 over n to the 3 halves. So this is convergent. So this converges by comparison. Or in a similar way, what if I had the sum, this is where things are going to start getting a little bit trickier, from n equals 5 to infinity of n squared over n cubed minus n plus 5. Okay, well, I started at 5 for a reason, because I can say that this is bigger than, so again, I'm thinking of comparing it to n squared over n cubed, which is 1 over n. Now the thing is, since I'm having subtraction and addition in the denominator, it's not super duper clear if this fraction is bigger or smaller than this fraction. But if I start at n equals 5, well, n squared over n cubed minus 5 plus 5 is just n squared over n cubed, so they're the same. And then if n is 6, n squared over n cubed minus 6 plus 5. So this denominator got smaller, which means this fraction is bigger. So this is technically greater than or equal to it, but right, really greater than, because we're adding up all the things. So it is bigger, but we had to do some checking. But then this is just the sum from n equals 5 to infinity of 1 over n. So this diverges by comparison, right? It is bigger than the thing that is divergent. Now, yeah, a couple more examples. I will tell you, the comparison test is not my favorite test. It is, but it is useful sometimes. Sometimes it is the only test that works, believe it or not. Usually, if you can use the comparison, you can also use the limit comparison, which we'll talk about in just a minute. What if I had this, 1 over n times 3 to the n? It's not bigger than 1 over n, right? It's definitely smaller than 1 over n. But it's also smaller than 1 over 3 to the n. This is definitely smaller than the sum from n equals 1 to infinity of 1 over 3 to the n. Right? Again, this denominator is bigger, so this fraction is smaller than that fraction. But this thing here, that's a geometric series. 1/3 to the n. So that's convergent, which means this converges by direct comparison. Oh, here's a good one. Oh, by the way, I just point out, I don't think anyone did the optional quiz, which is fine. No one had to do the optional quiz. I did post solutions to it though, so if you want to look at those at some point, you're certainly welcome to. They are on Canvas. Let's look at this one. The sum from the thing that made me think of it is this next question. The sum from n equals 1 to infinity of the inverse tangent of n over n squared. Right. So here's the thing about inverse tangent. And this is something you're going to want to know. It's going to come up a few times. And it's in the quiz. What's the limit as x goes to infinity of the inverse tangent of x? You may know this? Yeah, excellent. It's pi over 2. And more importantly, it's actually true also that inverse tangent is always less than or equal to pi over 2. If you graph inverse tangent, it looks like this, where with a horizontal asymptote at pi over 2 to the right and negative pi over 2 to the left. So, right, which is really, right, we're just taking the tangent graph and we're flipping it around, y equals x. So your vertical asymptotes from tangent becoming horizontal asymptotes, right? Yeah. So what's cool here is that this is less than the sum from n equals 1 to infinity of pi over 2 right squared. And then the pi over 2 constant can come out. And we can rewrite this as pi over 2 times the sum from n equals 1 to infinity of 1 over n squared. But this is a convergent p-series. Times a constant, still convergent. Or if it was divergent times a constant, still divergent. So that means this converges by comparison. Let me do one more. Oh yeah, it's good to know. What if I was doing the sum from, I don't know, the natural log of n over n from n equals 2 to infinity. We might have done this one last time. I don't remember. Maybe I put it on the quiz. It's true that the natural log of n is bigger than 1. So you could definitely do this with the integral test. It totally works, right? We definitely know how to integrate natural log of x over x with a u sub. But it's much easier to do this by just saying, oh, wait, this is bigger than 1 over n, or the sum of 1 over n, which is divergent. So it diverges by comparison. Right? We know this is divergent, and since this is bigger, it has to diverge. You could also show it diverges by doing this integral. But I don't want to. All right. So the problem is when we start having, no, actually, wait, one more, sorry. Sum from n equals, what did I get here? Sorry. N equals 1 to infinity of the natural log of n over n cubed. It is nice to know, so the natural log can kind of throw people off. It's really kind of worth knowing that the natural log of x is always less than x to any positive power. And I really kind of want to show you this to see, I think it's kind of cool. So let me show you on Desmos real quick, just because so you can see. I could draw it for you, but let's be real, Desmos is way, whoops, don't be stupid computer. Desmos is going to make a much nicer picture than I ever could. So if we check this out for just one sec, here's y equal to the natural log of x. And here is y equal to x to the 1 over, I wonder, oh, you know what I can do? This is gonna be cool. I can do a slider. So I don't just have to pick a value for p. I can add a slider for p. So then we can see, okay, so let's check it out. Let me zoom out a little bit. Okay, so clearly when p is 1, natural log of x is definitely less than y equals x, right? But if p equals, can I just go click it over? Yeah, oh, sure. So if p is, I want just numbers. Can I give myself a table here? Sorry, it's looking super funky, I know. So p is 2. I wonder if I can make this a table. No, probably not. Okay, fine. So, oh, there's a way to do this. Yeah. Cool. Yeah. So p is 2. No, I don't want that. Sorry. I'm screwing it all up. Apologies. I thought it was going to be cool with my table, but it's not. Let's just make it easy. So if we do 1 over 2, right, it is definitely hopefully clear that, oh yeah, the square root does get bigger, right, faster than the natural log. And that's actually true for any root, right? Whether it's the second power or the third root. I know it's kind of hard to see, but it is actually true. Right, so I will share that, oh yeah, the natural log actually does get bigger than the cube root for a minute. But if you go further right, they cross back over. And no matter what your root is, sorry, I know I'm kind of being silly here. No matter what your root is, eventually it's going to overtake the logarithm. Now I know it's even harder to see here, but right, so it definitely looks like, okay, well, my logarithm looks bigger, but you can kind of see the bend of the logarithm is just not going to increase quite as quickly as the root here. And I think zooming in or out is not really helpful, but it's actually true. And we know this because we know what the inverse functions do. We know that the inverse of the natural log of x is e to the x. And we know that the inverse of the fourth root of x is x to the fourth. And it's true, so just like it's true that this e to the x, although the fourth power of x is bigger for a while, we know in our hearts, and just we know that e to the x, the exponential function, eventually overtakes any polynomial. And so when you take the inverses, the relationship switches. So because e to the x is eventually larger than x to the fourth, we also know that the natural log of x is eventually smaller than the fourth root of x. So I think that's kind of cool. Let me stop sharing. So it is definitely true that I should say natural log of x is less than x to the p eventually. Eventually, the natural log of x is less than x to any positive power. So what does that tell us? Well, for this one's simple. We could just say it's less than the sum from n equals 1 to infinity of n over n cubed, which is just 1 over n squared, which converges. Converges. So this converges by comparison. But if I had to do something like, where'd you go? So the nice thing about the square root of x and x is that the natural log is directly less than them. For other powers, you do have to adjust a bit. But so for example, if I was going to do the sum from n equals 1 to infinity of the natural log of n over n squared, then I would want to say, oh, well, I know the natural log of n is definitely less than the square root of n. And this for sure is convergent because this is just 1 over n to the 3 halves, which converges as a p-series. All right. So the direct comparison test, while it's good when it works, it definitely has some limitations, which can be overcome if you really try hard, but there's a better way. So for example, this series, the sum from n equals 2 to infinity of n over n cubed minus 1. This certainly acts like the sum from n equals 2 to infinity of 1 over n squared. Right? It's very, very similar to that, except that not quite. But the problem is I can't really use the direct comparison test as is, because n over n cubed minus 1, this denominator got smaller, so that means it's bigger than n over n cubed, which is 1 over n squared. But being bigger than something that's convergent, right, if I say that this series is bigger than that series, that doesn't help me. If I am bigger than some finite number, I could be finite, I could be infinite. So the problem here is that you kind of really have to work hard to make this work using the comparison test. There are ways to do it. Like I'm trying to think of it now, and I think you can do something. I think it works. Do something like, say, I'm kind of guessing. I think you can say something like, well, n over n cubed minus 1 is maybe smaller than 2 over n squared. That seems reasonable, right? If you cross multiply, this is positive and this is positive. So when you cross multiply, if things are negative, you have to be super careful. Nothing's negative. So I get n cubed less than 2n cubed minus 2, right? Multiply this by this. And then I can subtract n cubed, add 2. This is true as long as n cubed is bigger than 2, which is certainly true here. So yeah, it is true that you have this. So we could directly compare this, the sum from n equals 2 to infinity of n over n cubed minus 1, with this, the sum from n equals 2 to infinity of 2 over n squared. And then you can pull out the 2 and say, oh, well, that's convergent. But you and I both know we don't want to have to work this hard to do it, right? It's usually much more complicated. Like sometimes things are like, so this leads us to the desire of the limit comparison test. So basically the limit comparison test says, and really the limit comparison test, I would say you use most of the time when you have these rational looking things. So for example, let me do the example and then I'll say what the limit comparison test is. So let's say I was trying to do this here, the sum from n equals 2 to infinity of 1 over, what was it? Oh, sorry, it was n over n cubed minus 1. So I'm going to limit compare with the known convergent series that is similar to this, the sum of n over n cubed, which is the sum of just 1 over n squared. Again, for both comparison and limit comparison, you still have to have an inkling of what you think is true about the series. I think the series is convergent, so I'm comparing it with something that's convergent. And as almost every time when it's a power of n over a power of n, you don't have anything else weird. You're just comparing the ratio of the highest power to the highest power. So I'm comparing it to n over n cubed, which is 1 over n squared. So here's how the limit comparison test works. You take the limit as n goes to infinity of the unknown sequence on top. Right? We don't know if this one converges or diverges, so I'm calling this the unknown one, divided by the known sequences on the bottom. We almost always take this, flip and multiply. So you get the limit as n goes to infinity of n over n cubed minus 1 times n squared over 1. And if you're using this for the right type of thing, you're always going to get something where the degree on top and the degree on the bottom are the same. So you get the limit as n goes to infinity of n cubed over n cubed minus 1, which is equal to 1. And as long as the limit you get using the limit comparison test is a real number, which this is, then this series and this series have the same behavior. So this is, I should say, well, I should back up. As long as you get a real non-zero number, then you can say that both series have the same behavior. And then there's two kind of caveats about that. So here's the limit comparison test. And I almost always use this test if I have rational looking things. Powers of n over powers of n, no other weird functions abound. So here's the limit comparison test. Here's what it says. So, yeah, sorry. Oh, interesting. That's an interesting way of writing it. I kind of like, so I like the way this person is written. I'm using Grant's notes as so to determine if the series with the sequence a sub n, if it is convergent or divergent, here's what we have. So let this be some other known series. I should say some other series whose behavior is known. Then we have two things. Thing one, if the known series converges, and the limit as n goes to infinity of the unknown sequence divided by the known sequence, the way this person is saying, if it's equal to L, which is not infinity, so basically if the limit is any non-infinite number, including 0, then this series also converges. And then on the other hand, if the known series diverges and this limit of the unknown over the known is equal to L, which is not 0, meaning if you're looking for divergence, it's okay for the limit comparison test to give you infinity, then the sum of A and N also diverges. So that's the whole gist of the limit comparison test. You take the limit of the unknown sequence over the known sequence. If the known sequence converges, then your limit has to be either 0 or a finite number to also show that your unknown one converges. If your known series diverges, then this limit has to be either a finite number or infinity for your unknown series to diverge. It's kind of a mouthful, but let's go ahead and do another one. It's all about knowing or having an idea of if your series converges or diverges. So for example, what if I wanted to say, how about the sum from n equals 1 to infinity of 3 to the n over n cubed? You could probably use the test for divergence here. You could probably get the limit of this is not 0, but that's actually kind of a bit of work. It's easier to use the limit comparison test. It isn't easier. I started thinking of another test. Yeah, maybe it's not easy. Sorry, I think I picked a bad example. Apologies. My brain was thinking of something else that we're not quite at yet. Sorry about that. Sometimes my brain does other things. So let's compare let's say we want to look at, say, the limit of 2n squared, let me make it smaller, minus 1 over n cubed plus n squared plus 5. This would be a pain to try and do directly, but I know that this is essentially acting like 1 over n. Or you could write it as 2 over n if you really wanted to. I kind of tend, if I'm thinking limit comparison, I tend to ignore the coefficients as well. So this, I'm just looking at that and that, the highest powers. So I'm going to say, all right, I'm going to limit compare with this, which is just that, which I know is divergent. So I've already decided I'm trying to show this thing diverges. Whatever I do here, my work will not show convergence because I'm comparing with something that diverges. So if I take the limit as n goes to infinity of, it's always the unknown on top. So 2n squared minus 1 over n cubed plus n squared plus 5 over the known one on the bottom, which is 1 over n. People often skip this first step and jump straight to multiplying by the reciprocal of the known one. So it's going to be the limit as n goes to infinity of 2n squared minus 1 over n cubed plus n squared plus 5 times n over 1, which is really just the limit as n goes to infinity of 2n cubed minus n over n cubed plus n squared plus 5. And this being a rational expression, the limit is just the quotient of the leading coefficients, which is 2 over 1, which is 2. And since I'm looking for divergence, the only thing I don't want to get is 0. This is not 0, so we're good. So since this diverges by limit comparison. Typically, it is good practice to state the test that you are using when you show something converges or diverges. So if you were saying something is convergent, it is usually a good idea on your homework or your test to say convergent by whatever test you use to show it's convergent. It's not required usually, but it is a good idea. Yeah. Here's a classic tricky one. Is that one? Yeah. So the limit n goes from 1 to infinity of sine of, we'll do both sine of 1 over n, and we'll also do sine of 1 over n squared. So this one really looks like trash. Unlike the cosine one that we did last class, this one we can't use the test for divergence. I mean, we could try, but the limit, I think our jackhammering outside is like, I hope you guys can't hear it, but it is super loud for me. I'm like, ugh. It's not as bad as when they were doing like the work in my own yard last year, but it's pretty loud. I think someone's putting in a pool. Anyway, not your problem, just my problem. So if we try to use the test for divergence, 1 over n goes to 0. Sine of 0 is a big old 0. That tells us nothing, right? The limit of the sequence is 0. It could converge, it could diverge. So, Also, direct comparison. So, I mean, obviously ratios out. Integral test is out. I don't know how to integrate sine of 1 over x. I don't think it's possible. It's not geometric. I think I said that already. Direct comparison. I know that sine is between 1 and -1. But that doesn't help. Here's what works. And this is one you have to kind of have seen to actually know how it works. So I'm going to do the limit comparison test with 1 over n. Look at what we get. The limit as n goes to infinity of sine of 1 over n over 1 over n. Well, there's two ways you can do this. First way, you can use the fact that you have sine of a thing over the same thing, and both those things are going to 0. And we know that the limit as x goes to 0 of sine x over x is equal to 1. So you really could just say this limit is equal to 1. But if you don't like that, and I get it, you can also use L'Hopital's rule and say, okay, that's the limit as n goes to infinity, because it is a 0 over 0 type. The derivative of 1 over n is negative 1 over n squared. The derivative of sine of 1 over n is cosine of 1 over n times the derivative of 1 over n, which is negative 1 over n squared. These cancel. And then the limit as n goes to infinity of cosine of 1 over n is going to be cosine of 1 over infinity, which is 0, which is 1. And since the limit isn't 0, isn't infinity, this series and this series have the same behavior, which is going to be divergent. So that's kind of a cool way of showing that this series, well, not just cool, kind of the only way of showing this series diverges. In exactly the same sort of way, you could, and I think you should when you have a moment, I'm not going to do it, but I feel like all of you can be like, oh yeah, of course, you should be able to show that the sum from n equals 1 to infinity of sine of 1 over n squared converges by limit comparison with the sum from n equals 1 to infinity of 1 over n squared. So it's exactly the same sort of work. You're going to do the limit. You can use L'Hopital's rule if you want. The limit's going to equal 1, but since this time you're limit comparing with something that is convergent, this is also going to converge. So kind of neat. I think it's neat. Let's see, where are we at? Oh, okay. Yeah, let's take a look at something that's a little bit harder. So I should ask, have you guys started talking about the ratio test yet? Okay, cool, that's fine. I might start anyway because ratio test is cool. Typically, if I'm trying to see if something converges, my go-to tests are usually either limit comparison, if it looks something like stuff with just powers of n over powers of n, maybe a natural log, or ratio test. Ratio test specifically if you have n as a power or a factorial. Whenever you have a factorial, ratio test is always kind of the go-to first test to try. But here I would try limit comparison. And I might start by limit comparison with 1 over the square root of n. Right? Sometimes I just kind of ignore the natural log. So when you're thinking limit comparison and you have a natural log, there are kind of two things you can do. You can either, one, ignore natural log. I can spell ignore, really. Or two, replace it with n to a power, n to a positive power. So, for example, if I ignore it, let's see what happens. So I'm going to say, I'm going to look at this. So I'm going to do the limit as n goes to infinity of the unknown square root of n times natural log of n. It seems kind of dumb to write this out every time, but I'm doing it so, right? I definitely think you all could skip this and go straight to, and not only can, should skip this and go straight to saying it's the limit as n goes to infinity of the unknown sequence times the reciprocal of the known sequence. I guess in this case, you also could have just said, I see those root n's are going to cancel. So I end up getting the limit of 1 over natural log of n, which is going to be 0. Now, in this case, that actually doesn't tell us anything because this series is divergent, right? It's a p series with p being less than or equal to 1. This is divergent. So that doesn't tell me anything, right? If you're limit comparing with something that's divergent and you get 0, back to the drawing board. So let's maybe it converges. Maybe I should try replacing the natural log of n with just n. So I could try a limit comparison with, let's see, the sum of 1 over square root of n times n is n to the 3 halves. So now with this series I'm comparing against, I'm trying to get convergence. So let's see if that works. So I'm going to have the limit. I'm going to follow my own advice here and do the unknown 1 over n to the 1/2 times the natural log of n times the reciprocal of the known series. So the reciprocal of this is n to the 3 halves over 1. N to the 3 halves divided by n to the 1/2 is just n. So we get the limit as n goes to infinity of n over the natural log of n. We know this limit's going to be infinity because we know that n outpaces natural log of n. To actually show it, you would use L'Hopital's rule. There is a lot of L'Hopital's rule in the limit comparison test. Or maybe not a lot, but certainly some. Derivative of n is 1. Derivative of natural log of n is 1 over n. Flip and multiply, you get the limit as n goes to infinity of n, which is infinity. Well, darn, that also doesn't tell us anything, right? I was looking for convergence, and I got the limit being infinity, which means back to the drawing board. So often, although I said, ignore it or replace it with n to a power, often the best choice of power to kind of quote unquote replace the natural log with is the square root of n. That is usually what I'm going to actually do for it. I just kind of want to show you two cases where you don't get a resolution, because I really want you guys to be prepared. Sometimes you're going to try a thing and you're going to get an inconclusive test. For the limit comparison test, it's when you're looking for divergence and get 0, or looking for convergence and get infinity. For the ratio test, it's totally different. For the ratio test, when you get 1 as your limit. Totally different than the limit comparison test. So I'm going to limit compare with this series, 1 over the square root of n times the square root of n, which is just 1 over n. So that means I'm looking for divergence, which means I want my limit to be anything except for 0. 0 is bad, everything else is good in this context. So I'm going to do the limit as n goes to infinity of the unknown, 1 over n to the 1/2 times the natural log of n times the known, times the reciprocal of the known, which is n over 1. n divided by n to the 1/2 is n to the 1/2. So I get the limit as n goes to infinity of n to the 1/2 over the natural log of n. Infinity over infinity, we use L'Hopital. Get the limit as n goes to infinity of the derivative of n to the 1/2 is 1/2 n to 1/2. It's amazing how you can say one thing and write down another thing. 1/2 n to the minus 1/2 over the derivative of the natural log of n, which is 1 over n. And simplifying that, I would say I have the limit as n goes to infinity of 1/2 times n to the minus 1/2 times n over 1, or just n. N to the minus 1/2 times n to the first is going to be the limit as n goes to infinity of 1/2 times n to the 1/2. If n goes to infinity, n to a positive power also goes to infinity. And infinity is all right. We said that 0 was the only thing we didn't want. We didn't get 0, we're good to go. So since this diverges, this also diverges. It's a bit of work. Yeah. Okay. Oh, I see. Yeah, we got time. Oh. All right. So the next test is kind of based on the geometric series. And so just as a reminder, right, here's a geometric sequence. So 24, 12, 6, 3, 3/2, 3/4, et cetera, et cetera, right? Clearly, each time we are multiplying by 1/2, right? 24 times 12. In fact, the way you can find the ratio is just divide the next term by the previous term. 12 over 24 is 1/2. 6 over 12 is 1/2. 3 over 6. Yeah, clearly it is a geometric sequence because every next number divided by every previous number is exactly 1/2. So here our ratio is 1/2. This is a, so I should say then the series, right? So the sum, 24 plus 12 plus 6 plus 3 plus 3/2, right? This infinite series, this infinite sum, is convergent. Because it is a geometric series with r equal to 1/2. And that's between 1 and -1. We could actually write out the sum of this if we wanted to. The formula, although you don't have to, right? You could totally just write it like this and say, look, it converges. The r is 1/2, and that's kind of all you need. But if you actually want to write the summation notation for it, you could write it out as, I would probably go the easiest way possible and say, I know my r is 1/2, so I'm going to have 1/2 to the n. And then if I start at n equals 0, I know I need a 24 here. So that's how you can write the formula for the geometric series pretty easily. right? The 0th term is 24 times 1/2 to the 0, which is 24 times 1, and then every subsequent term is 1/2 the size. There's something else I want to say here. No, that's it. So the idea here is that there are other series that, while not exactly geometric, are close enough to being geometric that we can kind of, what's the word I'm looking for? That we can use their geometricness. Which I know you're like, what are you saying, James? So here's what I'm saying. So let's look at, so let's say we had a sequence that wasn't exactly geometric. A1, A2, A3, A4, etc. N plus 1, and it just keeps going. So if the idea here is that, so just like in the previous slide, the ratio between each term is that, right? So here the ratio is A2 divided by A1. And here the ratio is A3 divided by A2. Always the next term divided by the previous term. So the idea here is that this is essentially the ratio. And if this an plus 1 over an, if the limit of it is actually equal to a ratio that is less than 1, then we're going to get convergence, because it's essentially like a geometric series where the ratio is less than 1. So here's the idea, or here's an example of the idea. Let's say we have this series, sum from n equals 1 to infinity of n squared over 2 to the n. And I would know right off the bat, after we talk about it, that I should use the ratio test here, which we haven't said what it is, because I have something to the nth power. So having something to the nth power or having a factorial are always good clues that we should probably use the ratio test. By probably, I mean definitely. So let's write out the first few terms. So I know we're not going to look super cool, but let's write them out anyway. So let's see, I'm super cool. Other sequence is very cool. This one, not so, like whatever. Okay, so sorry. So I get, let's see, 1 over 2, and then my next term is 4 over 4, and then my next term is 9 over 8, and then my next term is, if I plug in 4, I get 16 over 16. And this looks like it's kind of just going, right, it got bigger, it got smaller. But so these first few terms, okay, whatever. I don't really know what's happening with those. But if we go way out, like to the 1,000, or let's go 100th term. So we go to, like, say the 100th term being 100 squared over 2 to the 100th power. And the next term is going to be 101 squared over 2 to the 101st. And the next term is going to be 102 squared over 2 to the 102nd. You could ask yourself, this is essentially behaving geometrically, right? The top is not getting a lot bigger, whereas we're essentially multiplying by 1/2, right? If I say, so in fact, let's do the thing, right? If I look at this divided by this, so this divided by this is going to be 101 squared over 2 to the 101st. Dividing by this is like multiplying by the reciprocal. Sorry, this would be 101. Apologies. So check this out. 2 to the 101. Oh my God. These are the 101s. These are the hundreds. Apologies. Sorry. 2 to the 100th over 2 to the 101. All of them cancel except for one of the 2's in the denominator. So this is equal to 101 squared over 100 squared. And then 2 to the 100th over 2 to the 101st gives me 1/2. Well, 101 squared over 100 squared is essentially 1, right? This is 1.01 squared, which is 1.0201 times 1/2. So essentially, the ratio is 1/2 when we get out here, right? This times 1/2 is almost this, and this times 1/2 is almost this. And what we're going to see is that we can, in fact, that's what I did. So that's the whole idea. That the ratio here is essentially 1/2. Now, how do we actually do this without having to like rattle all these terms? Well, here's what we do. We're going to look at this, and then we're going to take the limit of it. So I wanted to kind of say all those things, though, to make it clear that the reason this ratio test works is because the ratio test is asking, does the series act like a geometric series? And if it does, is the ratio less than 1? Right? Because for a geometric series to converge, we need the ratio to be less than 1. So for this series here, which again is the sum from n equals 1 to infinity of, I forgot, n squared over 2 to the n, we're going to take the limit as n goes to infinity of the next term over the previous term, right? That's our ratio. And I think we actually have to have an absolute value here. Don't sweat the absolute value too much, but we do usually have an absolute value. So now I'm going to write things. It's going to be the limit as n goes to infinity of, so again, there's a lot of fractions, and almost all the time we just get in the habit of saying, okay, it's the top thing times the reciprocal of the bottom thing. So the a sub n plus 1 is going to be n plus 1 squared over 2 to the n plus 1. And the reciprocal of the bottom thing is going to be 2 to the n over n squared. And almost all the time when we do this, we group like things together in similar fractions. I don't need the absolute values anymore because everything here is positive. I'm going to rewrite this as the limit as n goes to infinity of, I'm going to group the 2's together. So 2 to the n over 2 to the n plus 1, that's just going to be 1 over 2, times n plus 1 squared over n squared, which is equal to the limit as n goes to infinity of 1 over 2 times, you can deal with this any way you want. I'm thinking of it as either n plus 1 over n quantity squared, which is really just 1 plus 1 over n squared, which is 1 as n goes to infinity squared. Or you could think of multiplying it out and seeing that it's n squared plus 2n plus 1 over n squared. Look, it's a rational function where the degree on top and the degree on the bottom are the same. So the limit is the quotient of the leading coefficients, which is just 1 over 1. So my limit here is 1/2 times 1, which is 1/2. And that's my ratio. My ratio is 1/2. And if my geometric series or my pseudo-geometric series, because it's not really geometric, but if my series that's acting like a geometric series has a ratio that's between 1 and -1, which is why I probably take the absolute value, right? This is definitely less than 1, which means we get convergence. Here's the nice thing about the ratio test. You don't have to know if you think the thing converges or diverges to start with. You just get to apply this test and then say, oh, if the ratio is less than 1, just like a geometric series, we get convergence. If the ratio is greater than 1, just like a geometric series, we get divergence. So that's kind of really, I had probably never really fully thought about it that way before, but it's a really nice connection to make. That the ratio test has the same conditions as the geometric series test because it's really the same idea. And in fact, you can use the ratio test. You shouldn't, but you can totally use the ratio test for an actual geometric series. It's kind of silly, but if you wanted to, you could say, okay, well, here's a geometric series. Let's write something, I don't know, let's make it not too terrible. 2 times 3/4 to the nth power. We know this is convergent because we've got a ratio that's less than 1, or I should say between 1 and -1. But if you use the ratio test, take the limit as n goes to infinity of a sub n plus 1 over a sub n. Right? It's always the next term over the previous term. And then that's the limit as n goes to infinity of, let's see, so n plus 1, I get 2 times 3/4 to the n plus 1 over 2 times 3/4 to the n. Cancel the 2's. 3 to the fourth over n plus 1, sorry, 3 to the fourth to the n plus 1 over 3 to the fourth. The n is just 3 to the fourth. So it's kind of really silly in that you don't actually need a limit because the ratio is just 3/4. But there you go. The ratio test for a geometric series will also tell you that the ratio is what the ratio is, 3/4 in this case, which means convergence because it's less than 1. So the ratio test is kind of great. Well, I should really say it's kind of great when it works. Like most tests, it's great when it works. It's not so great. I mean, it's fine if it doesn't work, but it's not super helpful. So here, here's the statement of the ratio test in all its glory. So ratio test. Limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. If that limit's equal to r, then we have 3 possible outcomes. If r is less than 1, convergence. If r is bigger than 1, divergence. And if r is equal to 1, it's inconclusive. Meaning you have to do something else. Try again. Meaning try something else, not try the same test again. That would be dumb. Okay. So, like I was saying, factorials are really the time when this test shines. Also powers of n. I should say, no, not powers of n. Things that are to the nth power is what I really meant to express with that statement that was said completely wrong. So for example, here's a series, the sum from n equals 1 to infinity of, what do I got here? N to the fourth times 3 to the n plus 1 over n factorial. And I want to know, does this thing converge or diverge? So I'll tell you, there are not a lot of tests that deal with factorials other than the ratio test. The ratio test is kind of like the one and sometimes only test for things that have factorials in them. And the reason there is because they work out super nice when you've got a factorial, which is great. So I'm going to do the limit as n goes to infinity of, so the n plus 1 thing is going to be n plus 1 to the fourth times 3 to the n plus 1 is n plus 2 over n plus 1 factorial times the reciprocal of this, n factorial over n to the fourth times 3 to the n plus 1. This should be in absolute values, but since everything is positive, we're not going to sweat it. The only time you really need to worry about the absolute values is if you've got something alternating, and then you just usually get rid of the alternating part and drop the absolute values. So we're going to group the like things together. So I'm going to write this as the limit as n goes to infinity of n plus 1 to the fourth over n to the fourth times 3 to the n plus 2 over 3 to the n plus 1. That's just going to be 3 times n factorial over n plus 1 factorial. And this is kind of the one that we need to deal with. So I'm going to write this again. Limit as n goes to infinity. I'm going to leave this as is because we'll see something kind of cool here in a second. 3 to the n plus 2 over 3 to the n plus 1 is just 3. And how does n factorial over n plus 1 factorial simplify? This is a really important question that comes up all the time. How can you make this? So what we can't do is just cancel the factorials, right? It's not just n over n plus 1. Does anybody know what this is? Or if I said, what's 6 factorial over 7 factorial? Could anyone tell me what that was? I know it's almost 3. You guys are like, we're almost done. You might have checked out. So here's the thing I really, really want you all to hear because it's important. 6 factorial over 7 factorial. Well, what is 6 factorial? It's 6 times 5 times 4 times 3 times 2 times 1. What's 7 factorial? It's 7 times 6 times 5 times, right, exactly. Everything except the 7 cancels out. Another way people often write this, instead of writing all of it out, is they say that it's equal to 6 factorial over 7 factorial is 7 times 6 factorial. And then this number and this number definitely cancel out. So n factorial over n plus 1 factorial is n factorial over, well, n plus 1 factorial is n plus 1 times all the smaller numbers, which is n factorial. You can't just cancel the factorial symbols, just like you couldn't cancel the square roots, right? If I said I had like square root of 4 over square root of 9, we couldn't cancel the square roots and say it was 4 over 9. That would be dumb. Same kind of deal here. But you can definitely cancel n factorial over n factorial. And then I can also cancel happenstance here, an n plus 1 here and an n plus 1 there. Oh, but now look, I have a rational function whose degree on top is less than the degree on the bottom. Right? If I multiply this out, it'd be n cubed plus 3n squared plus 3n plus 1. This is n to the 4th. And when the degree on top is less, the limit is 0. So our ratio is 0, which means that eventually when you got far enough, the next thing is way smaller than the previous thing, right? Everything is much smaller than the previous thing. That is definitely less than 1, which means this converges. I definitely want all of you to take this observation to heart. This comes up a lot. You need to get real comfortable with changing n plus 1 factorial into n plus 1 times n factorial. And then